A titration curve is the result of plotting the pH versus volume of titrant added to a sample. So remember last year when we did our titrations, our titrant is the thing that goes in a burette, our sample is in the Erlenmeyer flask. So with our indicator, we could also put in a pH meter that would measure our pH. And then what I can do is I can add my titrant at 1 ml intervals or 0.1 intermils or 1 drop intervals, and I can record the pH for each of those time frames. And I can then take it and plot pH versus volume of titrant and sketch the curve. Now, obviously we can't do the actual titrations, but what we can do is we can predict what the curve should look like based on theory. And when we're doing this, we need to look at 4 particular pHs. Okay? Our first one is going to be the initial pH. So this is a pH of my solution before I add any of the titrant or anything from the burette. My second pH of interest will be my final pH. This is after I pass my equivalency point and now I add a large amount of the titrant so that I get close to my final pH. Obviously our pH at our equivalency point and what we've been talking about in terms of pH of salt solutions will come into play here. And finally, another value that is of particular interest is our pH at 1/2 equivalency. So let's say it takes 50 mils to reach my equivalency point, so it's my pH at 25 mils. Okay. Now we're going to begin looking at this with the first combination of a strong acid with a strong base. Now for this combination, we would probably use bromothymol blue as our indicator. Okay. For our titration, we're going to take 50 milliliters of a 0.1 mole per liter HCl solution, and we're going to titrate it with a 0.1 mole per liter NaOH solution. We're not interested in trying to determine the concentration of either of our solutions here. What we're interested in is the shape of the curve. Okay? And so what we can do is we can easily calculate our initial pH, and this would just be of the HCl. Now, because we know it's a strong acid, concentration of my proton or hydronium ion is equal to the concentration of the HCl, and so I can easily calculate the pH. Okay, and so we can plot that value on our graph. So before any NaOH is added from the burette, the pH of my solution is 1. Now, when we're titrating this, we have our NaOH plus our HCl. Okay, and the first thing we can do is we can calculate our volume at our equivalency, because we need to know what volume my equivalency point will occur at. And so I can just use stoichiometry from last year to determine my volume. So volume of my acid times the concentration times my mole ratio divided by the concentration of the base. And we get that my equivalency point will occur at 50 milliliters. So now that we know the volume at which our equivalency point will occur, what about the pH? Now, you'll be tempted to say the pH is always 7 because it's been neutralized, but remember we talked last week about the impacts of ions in solution and what they can do to the pH of that solution, and whether or not they can cause a hydrolysis reaction. When we look at this example, at our equivalency point, all of my hydroxide has been consumed, all of my proton or hydronium ion has been consumed, and I'm only left with the products of the reactants. So I have NaCl and water. And we know that sodium ion, cation of a strong base, does not cause a hydrolysis reaction. Chloride is an anion of a strong acid, and it's too weak a conjugate base to cause a hydrolysis reaction. So in this case, we can say our pH at equivalency is 7. So I can plot that value. Now, when I look at 1/2 equivalency, okay, what this means is it occurs at the point where half of my acid has been consumed. So that means if it took 50 milliliters to consume all of my HCl, what would be my pH when I add 25 milliliters of NaOH? Okay. Well, I can determine my total moles of H+, I can determine my moles of OH minus, my moles of H plus that would be consumed, and you can see right here I'm left with half the number of moles of H plus as I start off with. Okay, and now I'm going to convert this back into a concentration. I now have not 50 mils that amount of moles is in, but I have the 50 mils of H plus the 25 mils of the solution of OH minus. So I get my concentration of my proton, and I can get my pH. Okay, and so right here already we can see that this violates one of the things that we might intuitively have thought. We might have thought that if my pH at the start is 1, my pH at equivalency is 7, when I'm halfway, my pH should be halfway, 4, but it's not. It's still down here. Okay. Now, what about our final pH? Let's say I add 100 mils of base. What we're going to find is that we approach the pH of my titrant. Except we're never going to quite reach that pH because there is a bit of dilution that's gone on. Now I know my titrant is a strong base, so my concentration of hydroxide is equal to that. So I can calculate my POH, which will allow me to get my pH. So I now have this. And now it might be tempted to join these points, my initial pH of 1, my final pH of about approximately 13, although I'll never quite get to 13, my pH of 7 at equivalency, and my pH at half equivalency of about 1.47, 1.5, with a straight line. But let's start adding points so that we can see visually what's going on. It might help us to connect our points. So what I've done is I've just calculated the pH at a variety of different points so that we could see what's going on. Okay, so with 10 mils, 20 mils, 30 mils, we can see that my pH still hasn't climbed very much. 35, it's starting to go up. Now I'm at 45 mils. I'm getting close to my equivalency point. And my pH is finally starting to rise significantly. So what we'll do is we'll now start adding my NaOH in smaller amounts. Rather than in 5 mils, I'll measure the pH at closer intervals. So I'm going to measure at 1 milliliter intervals. And we can see here now it's starting to rise. I hit my equivalency at 50. Oh, that's 49.5. Then we have our 50. And then now here's 50.5. Okay, and as we go past our equivalency point, we can see what our curve looks like, our shape, and we connect them with a point. And so this would be the shape of my titration curve for a strong acid that's had a strong base added to it.